Pre-Calc Nation. We are on day 4 of section 5.3, talking more about logarithmic functions. So today we're going to talk more about ln, what that function looks like, and how to actually use it in a calculator. I will do my best to explain the calculator buttons using my iPad, but during class, don't worry, we will talk about it as well. So this box right here is from our notes that we just did on day 3. Again, it's important to realize that ln just means log base e. So if you see it, don't get nervous. It's the same thing. It's just log base e. People write it as ln. So now we're going to look at what actually the graph looks like. So I have 3 different functions here. I wrote the 3 different equations, and then I have boxes about that important information. So let's start with the blue. So the blue is the ln function. Notice the domain is going to be everything to the right, so 0 to infinity, because there's going to be that asymptote right here. Graph that in here. We know that from our last video. So it's going to be 0 to infinity. The range for the blue doesn't have any restrictions, right? It's going to go on forever. It's going to have arrows. The x-intercept is right here. X-intercept is going to be at the point 1, 0. Y-intercept, it's never going to have one because that asymptote at x equals 0 is going to affect it. So there's going to be no y-intercept, and I kind of already jumped the gun. Asymptote is x equals 0, this blue dashed line here. Now another way to think of this y equals ln of x is actually if we put it into exponential form. We know the base is e, so we can rewrite it as e raised to the y power equals the argument. Those are equivalent. You could see it either way, and it's important to recognize that they're the same. Now we're going to change to the green function, which is y equals ln of x minus 1. Well, looking at the green, let's follow the table here. The domain, it's going to actually be affected right here by this dashed line. You'll see it says x equals 1, vertical asymptote. That affects this green ln of x minus 1. So the domain is now 1 to infinity. The range will have no restrictions on those y values. Your x-intercept is labeled for you. It's going to be moved over 1 unit from the one above. It will still not have a y-intercept because it's now even further from the y-axis, so that's not possible. Notice the asymptote is already written as x equals 1. Another way to look at this is the base raised to the exponent gives you the argument x minus 1. Let's do a little comparison really fast. If I'm comparing blue to green, notice the only thing different is this minus 1. Well, that minus 1, just like with all the other functions we've talked about, is going to shift the graph to the right 1. Remember, it's the opposite. I even can put the parentheses here if that helps you. It's going to be the opposite of negative. So it's going to go, instead of left, it's going to go to the right. Well, that meant your domain went 1 to the right. Your x-intercept moved 1 to the right because it was 1, 0. Now it's 2, 0. And your asymptote actually moves 1 to the right. So that pattern we can now use moving forward, just like we did with our other functions when we graphed. Now let's see this pink one. You're kind of probably thinking, okay, that minus 1 and then, ooh, a negative 1 on the outside. So you might already have an idea of what this graph's going to look like. We can verify it with our graph here, and now let's put in domain and range. So what's interesting about this one, if I want to rewrite it, the first thing you need to do is you have to add 1. Okay, if I'm transforming from log into exponential, you cannot have a random plus 1 hanging on your log. Now you're able to change this. It was base e raised to the y plus 1 equals x minus 1. Kind of interesting. Let's see what it does to our domain and range. Look at domain. It still has the same asymptote as the green function. Okay, that makes sense because both are moved to the right 1 unit. The range isn't affected. Those y values can go on forever. Now the x-intercept here. I am told that it's going to be e plus 1 comma 0. Let's make sure we can find that together. Okay, so I'm told that that's why I know it's from the graph. But if I do an xy table, I'm finding the x-intercept, which means y is 0. So if you go to this function, I'm going to go right here. If you plug in 0, you will get e to the first, right? E to the 0 plus 1 is 1 equals x minus 1. We're solving for x, so add 1 to both sides. E plus 1 would equal your x value. So this would be e plus 1. Very weird, yes it is, but remember e has a value. It's at 2.7 from our first notes, so it's still a value. Your y-intercept, it's still not going to happen because we're moved too far away from the x-axis, y-axis. And your asymptote is going to still be x equals 1. Now, let's compare this to the ones we have above. This minus 1 here does everything that the minus 1 in the green function did. It's going to shift everything to the right 1. But then notice that e raised to the y plus 1 is affecting kind of the stretch of it. So if you want to put more values in and see what it's going to look like in the end, go for it. But as long as you can tell these 3 graphs are very different, I'm going to kind of bubble the exponential, but they all are based on this blue parent function. Okay, good idea to know these restrictions as you graph to make sure you check your answer. Now we're going to actually use our calculators to solve the natural logarithmic function. So grab out your calculators. We are going to undo the base e. So think about when we're undoing subtraction, we do addition. Undo multiplication, you do division, right? So we're going to undo the facts. So if we actually, I'm going to rewrite it so that we can see it. If we apply ln to both sides, ln will undo that base. I'm going to show you what that's going to look like. It means your exponent, 2t minus 5, is going to be multiplied, because this part comes to the front, multiplied by ln of e. Realize the left side, there's no exponent, so this will still stay ln of 500, so the natural log of 5,000. Hello. Let's in our calculators right now show that these cancel each other out. If they undo each other, you should be left with a 1, right? Times 1. So let's head to our calculator. ln that button is on the left side, right above the stow button, right here. That's ln. E is found by pressing the second key, and mine is right above the division symbol. I'm going to close that parenthesis. If ln undoes E, I should get 1. Voila. So that's why I chose to use the natural log of both sides, because now this goes away. It's just 1. That means I'm left with 2t minus 5, that exponent, equaling ln of 5,000. Let's use our calculators for this part as well. I'm going to head back. You're going to press ln, that button above the stow on the left, type in 5,000, and you get a crazy decimal. That happens, okay? 8.5171. So I'm going to write, this is really 8.5171. I'm going to solve for t, so that means I'm going to add 5. Keep going, you'll divide by 2 to get t by itself to be about 6.759. Okay. Another way to do this, so I'm going to erase this, but you already have it written down, is instead of simplifying it right away, you could actually leave the 5,000. You can add 5 to it, divide by 2, right, following all those steps. And if you just type this in your calculator, you will get the correct answer as well. So it depends when you want to simplify. This is exact, so if it just wants exact, go ahead, leave the ln in it. And this is the approximate, those decimals. Big thing is ln undoes the E. So that's why we take that and apply it to both sides. Almost done. We're now going to solve an equation using exponential function and our graphing utility. So for this one, step A, it says use a graphing utility calculator to show the equation has exactly 1 root. Then estimate the root to the nearest 1/10. Okay, so part A, in your calculator, you're going to treat each side as its own equation. In other words, y1 is going to equal 10 raised to the x divided by 2. Your second equation is going to equal 16, because you're trying to find where they are equal. So what you would do on your calculator is go to your y equals, type in the first 10 raised to the x, it should be x divided by 2. 10 caret, you can do x divided by 2. Then the next line is 16. So when you go to graph it, you'll see you'll get this. And now my goal is to find where they cross. If you didn't get this, please press zoom standard. So zoom 6. That's always helpful. Kind of recenters your graph. But our goal is to find where they cross. So the buttons to do that, we've done this before, is second trace. You're going to choose the button that says intersection, which is option 5. And then you'll have to answer the question. First curve, second curve, guess, and it should pop out with the intersection point of x being about 2.41. Okay, please try this on your own. If you don't get it, then please ask during class. We want to make sure our calculators are performing properly. Then part B wants you to actually solve the entire thing, but algebraically. by rewriting it in logarithmic form. Okay, so right now I can tell I am in exponential form because I have that exponent. So my first thing is going to transform it into log. That means my base is going to be 10. Argument 16 is going to equal x over 2. Now my goal is to get x by itself. So realize all I need to do to get x by itself is multiply everything by 2, and then x will be by itself. You'll have x equals 2 log base 10 of 16. Okay, so that is the exact expression in terms of log. So I'm going to write that this is exact. Then it also wants the calculator approximation. So let me show you what that looks like on a calculator. I'm going to get out of here. I'm going to clear this. So I need to type 2 log. Now log always has a base of 10 unless specified. So if there's nothing there, it's always 10. So I know in this case this is 2 log base 10, it's already there. 16, and I get 2.408. I'm going to round that to just be 2.41, and that would be my approximate. And notice it matches what I did with the calculator. Match and match. So now you can check your calculator with your algebraic and your algebraic with your calculator. We'll do a lot more in class. Please bring questions.